So here's what we proved last time, that if you have F containing K containing L, and if K over F is a splitting field, then any automorphism of L, which fixes F, restricts to an automorphism of K. Now in this result, the hypothesis that K is a splitting field over F is absolutely crucial. Here's an example. So now, K being a splitting field over F is crucial here. So let's look at an example. Take L to be the splitting field. So let's take L to be in C, the splitting field of let's say x cubed minus 2. So this is now equal to Q adjoint a cube root of 2. Let's take the real one. Well, actually it doesn't matter. And then this guy times a omega, and then cube root of 2 times omega squared, where omega is a primitive third root of unity, let's say e to the power of 2 pi I over 3. Now, so you have consider the following diagram now. You've got, okay, so Q down here. Well, I'm going to take the identity now from Q to Q. And then, so take now Q adjoint cube root of 2 here. And here, look at Q adjoint another root of 2. Let's say that one. Okay, by lemma 50 of your textbook, by the way, lemma 50, theorem 51. Those two are sort of the foundation of everything that we're now doing. The key results, that's what it is. So, by lemma 50, there's a unique map from here to there. It's going to be an isomorphism which sends cube root of 2 to cube root of 2 times omega. So this sending a cube root of 2, so let's call this one maybe sigma. Sigma sending a cube root of 2 to cube root of 2 omega. But then, okay, so now if you look back at the proof of theorem 51, well, this extends to a map from K and extends to an automorphism of K. So by the proof of, I'm just going to write it like this. So now go back and look at the proof and see, you see what you'll see this. By proof of theorem 51, sigma extends, actually, just to sort of maybe keep it more consistent with the notation that we used when we gave the proof of theorem 51. Let me call this one maybe sigma hat. And then sigma hat sends this root of that polynomial to that one. And then by that proof of theorem 51, sigma hat extends to a sigma in the Galois group of L over Q. Sorry, K over Q, my apologies. There is no L. So K over Q. So I feel like I messed up my symbols at some point. Oh yeah, okay, okay. So I don't want to start the whole video again. So let me, if you don't mind, okay, we call L to be the splitting field. This should be L. My apologies. This is L. These two are L's. This is L. This is Q and that. So that's good. So by that proof, sigma hat extends to sigma the Galois group of L over Q. So now you get the sigma hat there. And now, why is this a counterexample to this statement? Well, for when you're not assuming that K over F is a splitting field, because see, now, well, this is your K. This is what you're taking as K. Take this one as K. This one as K. And now what you're saying is that sigma hat, well, it's an element of the Galois group of L over Q, which doesn't send K to itself. It sends K to another subfield. Right? If I take this root 2 to be the real third root of 2, then it's clear that this is not the same as that. This is contained in R, that one is not contained in R. So sigma hat, this automorphism of L over Q, doesn't send K to itself. Right? So, conclusion. In this statement here, in this proposition here, the fact that K over F is a splitting field is absolutely crucial to make sure that every automorphism of L that fixes F sends K to itself. Okay, very good. So now all of this, why did we talk about all of this? Because now I want to go back and go back to the situation for the cubic equation. For the cubic equation. So now suppose, so back to the cubic equation. Suppose you're in the following situation. F, a polynomial with coefficients in Q, degree 3, irreducible. Now, as we discussed, so the Galois group, so let's say K is the splitting field. The splitting field, so K contained in C, the splitting field of F over Q. Now, let's say alpha so there's two scenarios here, right? There's two scenarios. One scenario, so think about the roots of F. F has three distinct roots. Now, well, because it has degree 3, one of those roots is guaranteed to be real. The other two roots, well, what you know about them is that, complex conjugation is the set of all the three roots to themselves. It fixes the real root. The other two roots, well, either they are fixed or they are mapped to each other, or they are swapped by complex conjugation. If they are sent to themselves, that means that, well, all your roots are real. If they are swapped, it means that your other two roots are a complex and not real. Right? So there's two cases. Either F has three real roots, or one real root and two complex, not real, complex conjugate roots. roots which are complex conjugates of one another. Okay, let's work in the second scenario. Calculation of the Galois group in the second scenario is quite easy. In fact, we already did it for a particular polynomial f, and the general calculation, the general argument is exactly the same. So now, suppose f only has only one real root. Then, so let's call this one alpha. Okay, so now your picture is like this. This is K, this is Q adjoint alpha, this is Q, this is degree 3, splitting field, the Galois group of K over Q. You can naturally think of it as a subgroup of the symmetric group on the set of roots of F, well, of which there are 3. This has 6 elements. So this has 6 elements. This has order 6. It's isomorphic to S3. So now you see that the number of elements of the Galois group of K over Q, well, divides 6 by Lagrange. On the other hand, this